Hello, this is Sadbir. The topic of our discussion in this video is first order linear system of differential equation. In the classification of the differential equation are ordinary, first order and linear. Linear system of differential equation is of this form where you have two or more dependent variables and only one independent variable. And all the dependent variable are of degree 1, or in other words, they are linear. And all the derivatives are taken with respect to only one independent variable. For example, in this case, it is a t. So here I will give you one example of 2 by 2 linear system. So dx over dt is equal to 2x plus 3y. dy over dt is equal to 3x plus 2y. This is a 2 by 2 linear system of differential equation. It has two dependent variable x and y and one independent variable t. So this system also can be written in the matrix form. So you can write as a d over dt of this vector x and y, which is also the solution vector, and the matrix, which is a coefficient matrix 2, 3, 3, 2, and the multiplication by the solution vector x and y. Sometimes you write it like a x prime, the derivative written in the Leibniz notation as a prime, and then a as a matrix and x, where a is the coefficient matrix of the linear system of differential equation. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will learn how to solve the system of linear differential equation. It is a 3-step process. In step number 1, we will rewrite the systems in matrix form as dx over dt is equal to a, which is a coefficient matrix, times the solution vector x. Then we take the matrix A and compute the eigenvalues and eigenvector of this matrix. Let's suppose you have n pair of eigenvalues and eigenvector, and all the eigenvectors are linear independent. Then you can write the solution of this differential equation by this formula. Here I will take an example and I will show you that how to compute the general solution of this linear system of differential equation. This time I have a 2 by 2 system of linear differential equation. So in step number 1, I will rewrite this system as x prime, a coefficient matrix, which is this time 2, -2, -4, 0. And then the vector basically x, I can write it as a x1, x2. Or in other words, I can write it as a -2, -2, -4, 0 time vector x, where the vector x is x1, x2. It's a column vector. In step number 2, we will calculate the eigenvalues and eigenvector of this matrix. Let's suppose this matrix is a -2, -2, -4, 0. So to compute the eigenvalue of this matrix, you will compute the determinant of A minus lambda I, and you will set that equal to 0. So let's calculate the determinant of 2 minus 2 lambda minus 2 minus 4 minus lambda and set that equal to 0. So this is going to be -2 lambda multiplied by minus lambda minus 8 is equal to 0. If you simplify this quadratic equations and find its roots, so its roots are 2 and 4. So next we have to find the eigenvector which are corresponding to the eigenvalue 2 and the eigenvalue -4. So let's take the first one. When eigenvalue is 2, so we will find the corresponding eigenvector. So first we calculate A minus 2 time identity matrix, and this matrix is -4, -2, -4, -2. And if you reduce that into row reduce echelon form, you will get a matrix 1, 1, half, 0, 0. So as you can see, this is the pivotal position and this is a free column, the free x2. I can choose x2 as a 1, and then my first equation gonna gives me x1 plus 1 half x2 is equal to 0. So if I plug x2 is equal to 1 here, so that give me x1 is equal to 1 half, -1 half. Therefore, my first eigenvector is x1 is a -1 half and x2 is 1. So this is my first eigenvector, which is corresponding to the eigenvalue lambda is equal to 2. Now I will find the second eigenvector, which is corresponding to the eigenvalue lambda is equal to -4. So the process is simple. For the first, you calculate A minus 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 plus 4 time identity matrix. So the row reduced echelon form of this matrix is 1, -1, 0, 0. This is a pivotal column and this is a free column. So x2 can be chosen freely. I choose x2 is equal to 1. So I can see that x1 minus x2 is equal to 0 from the first row. Therefore, x1 is also 1. So this implies my second eigenvector, which is a v2, is 1, 1. In order to check whether they are linear independent, I will put that into a matrix, v1, v2, and I calculate the determinant of that. If the determinant of this is non-zero, it means v1 and v2, they are linear independent. So let's check whether the determinant of this matrix 1 half, 1 and 1 comma 1, it is non-zero. So what is the determinant? This is a -1 half minus 1. So clearly this is a -3 half, which is not equal to 0. So my vector v1 and v2, they are linear independent. So I have a 2 by 2 system. I have a 2 linear independent system. So I can write down my solution. So the general solution of my differential equations will be x1, x2 is equal to c1 e to the power, the eigenvalue, which is a 2t, multiplied by the corresponding eigenvector, which is a v1, 1 half time 1, plus constant c2. The eigenvector is this eigenvalue is -4t, and I multiply by the eigenvector, which is 1, 1. So this is my general solutions of my 2 by 2 linear system of differential equation. Let's take one more problem. In this problem, so we will solve the 3 by 3 system of linear differential equation. So first I write the system of a linear differential equation in the matrix form as x prime, where x is a column vector x1, x2, x3, -4, 1, -1, -1, -2, 5, -3, 3, and 0 time x, where x is a solution vector, which is a x1, x2, x3. So in step number 2, I will calculate the eigenvalues and eigenvector of this 3 by 3 matrix A. So in the previous video, we have learned how to calculate the eigenvalues and eigenvector of a 3 by 3 matrix. Please review that video. So here we have 3 eigenvalue, lambda 1 is equal to 3, lambda 2 is equal to -3, and lambda 3 is equal to -6. And the corresponding eigenvector v1 corresponding to the eigenvalue lambda 1 is 0, 1, 1. Corresponding to the eigenvalue lambda is equal to negative 3, it is 1, 1, 0. And corresponding to the last eigenvalue lambda is equal to negative 6, the eigenvectors is 1, negative 1, and 1. So next we will verify that the vector v1, v2, and v3, they are linear independent by calculating the determinant of this matrix 1, 0, 1, 1, 1, 1, 0, 1, negative 1, 1. So the determinant of this matrix is a negative 3, which is a non-zero. So therefore all, we write down the solution x1, x2, x3 as c1 e raised to power the first eigen value, which is a 3t, multiplied by the corresponding eigenvector 1, 0, 1, 1, plus c2 e raised to power negative 3t, and the corresponding eigenvector is 1, 1, 0, and you can say c3 e raised to power negative 6, and the corresponding eigenvector is a 1, negative 1, 1. So this is our general solutions of the system of linear differential equation. Next, we have also given, we have to find a special solution when t is 0. Our solution should satisfy this vector 1, negative 2, 3. So let's compute the constant c1, c2, c3 in this special situation. So we have given when t is 0, our x vector is 1, negative 2, 3. This implies if I plug 0 here, so e to the power 0 is a 1, so I'm gonna get to 0, 1, 1 times c1 plus c2. This time I will get 1, 1, 0, and this is a c3, and then I get 1, negative 1, 1, and this is equal to the vector 1, negative 2, and 3. So now this can also be written as the linear system 0, 1, 1 in a matrix form 1, 1, 0, 1, negative 1, 1 times c1, c2, c3 is equal to 1, negative 2, 3. So here using the Gauss-Jordan elimination, we can find the value c1, c2, c3. So they are c1 is equal to 2, c2 is equal to negative 1, and c3 is equal to 1. So if you plug that values of c1, c2, c3 back into the general solution, it will give you the special solution of this system of linear differential equation. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and practice on this problem. Next, in this examples, we will learn that how to solve the system of linear differential equations when it has a repeated eigenvalue, or in other words, when we have fewer independent eigenvector corresponding to one eigenvalue. Here the system of linear differential equation is already written in the matrix form. So I will begin by calculating the eigenvalue of this matrix A. So clearly the eigenvalues of this matrix A, you can calculate. They are repeated, they are 3 and 3. So if I calculate the corresponding eigenvector corresponding to this repeated eigenvalue, what I have to do is I have to solve this system A minus 3i x is equal to 0, or in other words, I have to solve this system, which is a negative 2, 4, negative 1, and 2 time x1, x2 is equal to 0. If I use the row reduced echelon form, I will get, this is a 1, this is a negative 2, 0, 0, and x1, x2 is equal to 0, 0. Therefore, this is a pivot variable and this is a free column. So here is the pivotal column. This is a free column. I can choose the free variable as x is equal to, maybe x2 is equal to 1. So if I solve this one, x1 minus 2 time of x2 is equal to 0. So if I plug x2 is equal to 1, so my x1 will be 2. So I got one eigenvector which is 2 and 1. I have a 2 eigenvalue and I have only one eigenvector corresponding to these two eigenvalues. So I need to find one more eigenvector which is a also linear independent to this the eigenvector which I have calculated. So now next find one more eigenvector. We will solve the system A minus 3i. Let's suppose u is the new eigenvector I want to find, and I set that thing is equal to v1 this time. So what it will be, so this will give, I mean, -2, 4, -1, 2. Let's suppose u1 has component u1 and u2, and my matrix V is, my column V is 2, 1. Or if I use the Gauss-Jordan elimination, so I will get -2, 4, 0, 0, which is a u1, u2 is equal to 2 and 0. So this system of linear equations has infinite many solutions. So you can see that if I multiply them, this is going to get 2u1 plus 4 times u2 is equal to 2. So since u2 or the second column is a free column, I can choose free column u2 is equal to, suppose, 1, and I calculate u1. So my u1 will be also 1. So therefore, my second eigenvector, which is 1, 1. We can also verify that this vector, they are linear independent. So by computing the determinant of 2, 1, 1, 1. So this is a 2 minus 1, which is a 1, which is a not equal to 0. So these two vectors are linear independent. So next we will write down the general solution. So in order to write the general solutions, you will write x1, x2. It's a different form than the one we have the linear independent. So C1, our first eigenvector is 2, 1. And when you write down the general solution for the second eigenvector, so you have to write t time the first eigenvector 2, 1 plus the second eigenvector, which is a 1, 1, which is also called sometimes the generalized eigenvector of the matrix A. So now this is our general solutions in this example, which has a very different form than the one we did in the very first example. Here I have one more quiz problem for you to practice. Please pause the video and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.